All right, welcome to our intro notes into reaction rates. We are going to start with a warm-up question to get your brains going because it kind of links into chemical reactions and how fast they go. First question is two factors that affect solubility. And remember, solubility is how much will dissolve. Is it just a little bit or is it a lot that will dissolve in your water? And you can remember that it ties into one, what the substance is, and also the temperature at which you're dissolving it. The second part of this is list three factors that affect the rate, the time. And we had a previous inquiry lab where we figured out that temperature has an inverse relationship. If you increase temperature, the rate goes down. When the time goes down, the rate goes up. Sorry. And then we had agitation or stirring. So as we stir it, it dissolves faster. And then we also had particle size. Now you may have noticed that chemical reactions, guess what? They have a relationship with these variables as well. And that's what we were going to see. That's what you did see in the lab. So what we're going to talk about is the four factors that influence rate. So now when we do a chemical reaction, there's one additional one that we're going to talk about that's going to affect how fast the reaction goes. So let's start with collision theory, all about those collisions. And same as before, atoms, ions, and molecules only react when they collide with one another. So it's no longer just about putting them into solution, but now it's about actually breaking bonds and forming new ones. And we have to have this term called an effective collision. And that means it's a collision that will actually produce a reaction. Because you can have ineffective collisions that do nothing. The atoms and molecules just bounce off one another. Just think about two cars driving down a residential area, 25 miles an hour, head-on collision. You're going to break some bumpers, get some little sore neck and whiplash, but not much will happen. However, if you're traveling down the freeway at 80 miles an hour and head-on collision, you're going to have a pretty darn big explosion, lots of energy involved in that collision. And that's going to tie into what an effective collision has. It has to have enough energy, and that's like the cars going 80 miles an hour versus 25. So that's what we call activation energy. They have to have enough energy to activate the reaction and break the bonds. And two, they have to be oriented in the correct way. If you have the wrong atoms actually doing the collision in the molecule, nothing is going to happen. Let's talk about that activation energy part first. It's the energy needed by those particles to overcome the bump and actually get the products. So if it's too low, all they do is bounce off one another, kind of like the cars going at 25 miles an hour, little bumper cars. No reaction will happen. If we do get the molecules moving high enough, the molecules will break apart. You'll break bonds and you'll form new ones, and we will get a reaction. This is what we want. We want that reaction to occur. When you're talking about an exothermic reaction, and this ties back into our last unit in thermo, your reactants are higher, your products are lower. So you have an overall negative delta H. You remember that? Now, these reactions don't just happen, though. They sit there for some time, and even though it would lose energy, become more stable over here in the products, lower energy, it doesn't happen all the time or right away. And that's because we do have a barrier to the reaction. This EA right here, this is your activation energy. To go from where the reactants are up to the top of that barrier, that costs you energy. And this is the spot where you have your atoms and molecules starting to break bonds and form new ones, and it's an unstable state for them to be in. We call that the activated complex or the transition state. So it costs us energy to get up into that highly unstable spot, and then new bonds can form and you fall down to where the products are. So in an endothermic reaction, let's see if I can erase a little bit of that for you. In an endothermic reaction, your reactants are starting lower and products are higher. Now, this is not necessarily favorable, but if we do want it to happen, we have to get these reactants all the way up to the top right here. So here you see the activation energy listed over here. A lot of the times you'll see it listed like this as well. This is a very common way to see it. So you see the activation energy within the graph part itself. So you give them a lot of energy to the top of where the activated complex is, and then they relax and release a little bit of energy to get to the products, which are still higher in energy than the reactants. So this is where we have our positive delta H. Let's talk about the orientation part. We do have to have the correct three-dimensional spatial orientation. If it's the wrong position, you will not have an effective collision. They're going to bounce off one another, and that's going to have no reaction. We call that an ineffective collision. And in this example, this would be a single replacement reaction. And so if you remember with single replacements, we want similar species to replace one another. Well, what's more similar to A, B, or C? It's going to be B. We want A and B to switch places. But if this approaches the other molecule, where A is going to collide with C, you're going to have no reaction. However, molecules move and twist, and so maybe the next time they collide, this molecule is now in a spatial orientation where A and B will collide and touch each other, forming a new bond here, AB, and this bond right here breaks. That was what we would call an effective collision. All right, let's quickly talk about those four factors and that affect the rate. And this is talking about time. How fast does it occur? First one is temperature. We'll go into detail in a second. Particle size. Concentration, which is pressure for gases because they're more soluble, and something we call catalyst. All right, let's talk about our temperature factor first. If you increase the temperature, and you should have seen this in the lab the past couple of days, if you increase the temperature, what you're really going to be doing is increasing your kinetic energy. So your molecules are moving faster. If they're moving faster, two things happen. One, you have more collisions. Because they're moving faster, they're just going to collide more often. It's kind of like versus, and not only that, the more collisions you have, the more likely you're going to have one that will be above the activation energy. And at a higher temperature, you will have more moving faster that are already above the activation energy. So your rate increases. Increased temperature, increased rate, direct relationship. Great graph here. What we have here is basically number of particles on the y-axis, or fraction of collisions, and the energy or temperature here I'm sorry, that's the y-axis, on the x-axis. The blue line represents a cooler sample. Say, I don't know, 10 grams of something. Maybe it's your cold Alka-Seltzer, water. A lot of those collisions are way down here, too low, but our activation energy is way up here. So if you look at the blue line, it's a very small region that actually has enough energy to break any bonds. If you warm that same sample up, you're going to see a shift out and a shift down in the way the curve looks, because it's the same area under the curve. We're increasing the temperature, so more molecules, the area under this curve, have enough energy to overcome the activation energy, so we will have more collisions at the right orientation and speed. Just think back to food. I mean, why do we put food in the fridge? I mean, the common answer we all know is to keep it from spoiling, but what are you really doing by putting it in the fridge? What you're really doing is basically shifting all those molecules down to a lower energy, so that way their collisions and their decay, you have a smaller area, fewer of them are going to have enough activation energy to break bonds and rot and produce other compounds. So the fridge is basically just lowering the temperature so that way the rate of decomposition slows down chemical reactions. Next thing is particle size, and you should have seen that as well in the lab. Smaller the particle size for the same mass sample, what you're really doing is exposing more surface area, thereby increasing the number of collisions. More effective collisions, rate increases. Easy peasy. So here this would be like your solid Alka-Seltzer tablet, and the water can only hit the outside of it. That's it. Can only hit the outside. So all of these molecules in here are protected. So it takes longer for the reaction to occur. But when you break it up into the crumbles or the powder, now the water can get on the outside and it can get on the inside, and so more collisions, increasing the rate. Third factor is concentration. This is basically just if you increase the concentration, and we learned this in our solutions unit, all you're doing is dissolving more moles in the same volume of water. So if you have more moles, you're going to have those particles squished closer together. If you have a smaller path between the particles, they're going to collide more often. More collisions more often means the rate is going to increase. So this diagram shows you, here's a low concentration. Let's see, do through my mouse. Low concentration. So a particle has to travel kind of a long distance before it actually has a collision. And remember, those collisions aren't guaranteed to produce a reaction. It may not be effective. So it has to travel a long distance. But as you increase the concentration, notice the mean free path, or the average path between a collision, decreases. The smaller the path, the more often you have collisions, the rate is going to increase. And the last factor we're going to talk about is a catalyst. What a catalyst does is it increases the speed without being consumed. Well, how does it do that? That's the big thing. When you add a catalyst, what you're really doing is providing an alternate pathway to the reaction. Rather than, like, let's say you're coming up to school, and instead of going, let's say you live down Newport, instead of going up Newport and making a left-on dodge into the parking lot, maybe you go on hold to 17th and to Hughes, and then to Foothill because there's less traffic, and so you get there faster. Basically, it's just an alternate pathway. Lowers the energy it takes to get to the products. Since it lowers the energy, more effective collisions, your rate increases. And this is an important graph. We see this graph all the time in chemistry when we're talking about catalysts. This would be an exothermic reaction because our reactants are decreasing energy down to the products, but every reaction has an activation energy. So the blue line is your normal curve, really high barrier. The reaction's not going to happen very easily. So we need the products. What we do is we find a catalyst that will provide that alternate pathway, and it does a fabulous thing. It lowers that barrier. And if it requires less energy to get over that barrier, then we're going to have more effective collisions that can actually make it to this point as compared to this point. More effective collisions, your rate is going to increase. This is an example of a catalyst. You may not know it, but you have catalysts all over the place in everyday life. This one is showing the example of a hydrogenation of an ethene molecule, C2H4. It's a double bonded carbon with a hydrogen molecule. Now think about these gases. Normally are going so fast and are so far apart from one another, they would barely ever see one another. So to get this hydrogen to bond in there would be almost impossible. But we provide a metal surface, usually like platinum or nickel, something that's not very reactive. And the ethene will bond down onto the metal surface, and so will the hydrogen. The hydrogen's bond breaks. This little lonely hydrogen then comes over, and because they're on the same surface, it's very easy for it to find it, forms a new bond. So now notice we have our new hydrogen here. The other hydrogen will find its way, forming another carbon-hydrogen bond, and now our final product is C2H6. Again, normally they wouldn't find each other in the gaseous state, but providing a localized place where they both adhere down to, we can get the reaction going. That's an example of a catalyst. That's like that alternate pathway. One that you might be aware of or not aware of is your cars. We have catalytic converters, and it's basically just a surface that provides a catalyst, a way for all these toxic, noxious gases that kill us. We basically pump them through this pipe that has this huge, like, meshy surface area thing, lots and lots of surface area. These gases that would normally just get spewed and sprayed out into the atmosphere adhere down onto the surface, kind of like the slide you just saw, and then they're converted into other things. So carbon monoxide, which would kill us, is converted to carbon dioxide. Nitrogen monoxide, which is a very reactive compound that breaks down the ozone, into nitrogen and oxygen, etc. So without catalysts, we would be, as you guys all know, dead. And that is pretty much it. We're not going to do the section quiz, but we can talk about it. In a chemical reaction, the energy of the reactants is always, is it greater than the energy of the products? Well, not always. Sometimes it's an endothermic reaction. More than the activation energy, less than the activation energy, less than the energy of the products. Well, the best answer here is going to be less than the activation energy, because we always have our reactants and then the bump, whether it's an exothermic reaction or an endothermic reaction. No matter what, the reactants will be lower. Number 2, an increase in which of the following will not increase how fast the reaction occurs? Temperature, concentration, total mass, or surface area? What do we think? The correct answer is total mass, because remember, temperature, concentration, surface area are all part of how fast the reaction goes. Third one, a catalyst works because it A, lowers activation energy, increases temperature, is temporarily or permanently changed in a reaction, or supplies energy. And the correct answer, drum roll, is it lowers our activation energy. So if we had a reaction pathway with a huge activation energy from reactants to products, the catalyst would simply lower that and make the reaction easier to happen. And that's it. Your homework tonight is going to be, well, you probably have already got it done, the blue packet, page 1 and 2 in the collision theory worksheet. And then you continue working on your lab. And you do have that extension for our lab last week, Friday at midnight.